Look up at the night sky, and you're seeing more than just distant pinpricks of light. You're witnessing the grand stage of stellar life and death. Hidden within those vast stretches of darkness are swirling clouds of cosmic gas and dust, glowing with colors so vibrant they seem almost unreal. These are nebulae, the universe's most breathtaking nurseries and graveyards, where stars are born in fiery cradles and meet their explosive ends in spectacular displays of energy. But what exactly happens inside these celestial marvels? How do they shape the destiny of stars? And what secrets do they hold about the cosmos itself? Picture this: a single nebula can stretch light years across, cradling enough material to form thousands of new stars. Within these colossal clouds, gravity works its magic, pulling together dust and gas until the pressure ignites a newborn star. But it's not just about beginnings. Nebulae also bear witness to the dramatic final acts of massive stars as they erupt into supernova, scattering their remains across space to fuel future generations. These cosmic cycles of creation and destruction are more than just distant phenomena. They're the very processes that forge the elements making up our planet, our bodies, even the air we breathe. This journey will take you deep into the heart of these interstellar wonders, where science and spectacle collide. We'll unravel how nebulae light up the darkness with their ethereal glow, why some resemble ghostly faces or towering pillars, and what they tell us about the fate of our own sun. Along the way, you'll discover how astronomers peer into these clouds to decode the universe's most profound mysteries. So buckle up, we're about to dive into a world where stars are born, where death gives way to new life, and where the cosmos reveals its most dazzling secrets. The story of nebulae isn't just about distant space, it's about the very fabric of existence itself. And trust me, you won't want to miss a single moment of it. Deep within the swirling chaos of a nebula, something extraordinary happens. The quiet, relentless pull of gravity begins stitching together the universe's next generation of stars. These stellar nurseries are anything but gentle. They're dynamic, turbulent places where gas and dust collide, compress, and eventually ignite under unimaginable pressure. Take the Orion Nebula, for instance, a glowing tapestry of cosmic material just 1,500 light-years away. Through telescopes, we can actually witness infant stars flickering to life within its folds, their faint light piercing through veils of dust like fireflies in fog. But how does a cloud of scattered particles transform into a blazing star? It starts with a tiny disturbance, a ripple in the nebula's fabric, perhaps from a nearby supernova's shockwave or the brush of a passing star. That ripple triggers a cascade. Gravity seizes the opportunity, pulling particles closer until they form dense knots called protostars. Over hundreds of thousands of years, these knots grow hotter and denser, until the pressure at their cores becomes so intense that hydrogen atoms begin fusing into helium. That moment when nuclear fusion ignites is the star's first true breath of light. What's fascinating is how these nurseries sculpt their surroundings. Magnetic fields twist through the gas like invisible threads, while radiation from newborn stars carves out cavities, creating those haunting, pillar-like structures we see in images. The Eagle Nebula's pillars of creation might be the most famous example, towering columns where stars are still forming, hidden within their dusty shrouds. These shapes aren't just beautiful, they're clues. By studying them, astronomers decode the forces that govern star formation, from the turbulence of the gas to the way newborn stars influence their siblings. And here's the breathtaking part: the material left over from star birth doesn't just vanish. It becomes part of the next cycle planets, asteroids, or even the building blocks for future stars. Our own solar system likely began in a nebula much like Orion, its dust grains eventually clumping together to form Earth and everything on it. So when you gaze at these cosmic nurseries, you're not just seeing the birthplace of stars, you're looking at the origin story of everything. While all nebulae share a cosmic origin, their appearances and behaviors couldn't be more different. Take Emission Nebulae, for example. These are the showstoppers of the universe, glowing with dazzling reds and pinks as if painted by an artist's brush. The secret behind their brilliance lies in the intense ultraviolet radiation blasting from nearby young stars. This energy excites the nebula's hydrogen gas, causing it to emit its own light, much like a neon sign flickering to life. The Orion Nebula is a perfect example, its radiant glow visible even to the naked eye under dark skies. But it's not just about beauty. These regions are powerhouses of star formation, where the very same radiation that lights them up also helps compress nearby gas, triggering the birth of new stars. Then there are reflection nebulae, the quieter cousins of their glowing counterparts. Instead of producing their own light, they act like cosmic mirrors, scattering the blue light of nearby stars. This scattering effect, similar to why our sky appears blue, gives these nebulae their signature ethereal glow. The Witch Head Nebula, draped across the constellation Orion, is a stunning example, its wispy tendrils of dust reflecting starlight like fog catching the beams of a distant lighthouse. What makes reflection nebulae particularly fascinating is their composition. They are often filled with fine dust grains, the same kind that eventually clumps together to form planets. So when we study these shimmering blue clouds, we're essentially peering into the raw materials of future solar systems. And then there are the dark nebulae, shadowy, almost ghostly structures that stand in stark contrast to their luminous neighbors. These dense clouds of gas and dust are so thick they block the light from stars behind them, carving out silhouettes against the brighter backdrop of space. The Horsehead Nebula is perhaps the most iconic, its distinctive shape resembling a stallion's head emerging from the cosmic depths. But don't let their darkness fool you, these nebulae are anything but empty. Inside their murky folds, gravity is hard at work, pulling particles together in slow, silent motions that will one day ignite into new stars. In many ways, dark nebulae are the universe's hidden workshops, where the next generation of stars is quietly being assembled. What ties these three types together is their role in the grand cycle of stellar life. Emission nebulae mark the fiery birthplaces of stars, reflection nebulae reveal the delicate dust that builds planets, and dark nebulae hide the earliest stages of star formation within their Inky depths. Together, they paint a complete picture of how the cosmos transforms raw materials into the celestial bodies we see today. And by understanding their differences, we gain a deeper appreciation for the dynamic, ever-changing nature of our universe, one where light and shadow dance in an endless cosmic ballet. Hydrogen might seem like just another element on the periodic table, but in the cosmos, it's the lifeblood of creation. Picture it as the universe's most basic building block, light, abundant, and deceptively simple. Yet within the swirling depths of a nebula, hydrogen becomes something extraordinary, the raw fuel that births stars and illuminates the darkness. In fact, over 90% of the atoms in these cosmic clouds are hydrogen, left over from the explosive beginnings of the universe itself. When gravity pulls these atoms together, they don't just clump, they transform. Under crushing pressure and searing heat, hydrogen nuclei collide with such force that they fuse, releasing unimaginable energy in the process. This isn't just chemistry, it's the alchemy that lights up the cosmos. The vibrant red hues of nebulae like the Lagoon or the Carina Nebula aren't just for show, they're hydrogen's calling card. As young, massive stars flood their surroundings with ultraviolet radiation, they energize the surrounding hydrogen gas, causing its electrons to jump to higher energy levels. When those electrons settle back down, they release photons of light, painting the nebula in shades of crimson and pink. It's a bit like a cosmic neon sign, where hydrogen is the gas inside the tube, glowing fiercely under an invisible current. But this light isn't just beautiful, it's a beacon signaling regions where star formation is in full swing. What's truly remarkable is how hydrogen ties the universe together. Without it, there would be no stars, no nuclear furnaces to forge heavier elements, no heat and light to nurture planets, no water or organic molecules to spark life. Every carbon atom in your body, every breath of oxygen you take, traces its origins back to hydrogen fused in the heart of a star. Even the water in Earth's oceans was once part of a nebula's hydrogen clouds, drifting through space until gravity sculpted it into our world. Hydrogen's journey from the Big Bang to your fingertips is a testament to the interconnectedness of everything in the cosmos. And yet, hydrogen's story doesn't end with star birth. When massive stars die in supernova explosions, they scatter their hydrogen-rich remains back into space, seeding future nebulae with the ingredients for new stars. It's a cycle as old as time, one that ensures the universe never runs out of stellar fuel. But hidden within this cycle is another secret: the birth of elements far heavier than hydrogen. Deep in the hearts of dying stars, under conditions even more extreme than those in nebulae, hydrogen's fusion gives way to the creation of carbon, oxygen, iron, and all the other elements that make planets and life possible. Supernova are the universe's ultimate alchemists, violent, brilliant, and astonishingly creative. When a massive star, many times heavier than our Sun, reaches the end of its life, it doesn't fade quietly. Instead, it unleashes a cataclysmic explosion so powerful it can outshine entire galaxies for weeks. This is the moment when the star's core collapses under its own gravity, rebounding in a shockwave that rips through its outer layers, blasting them into space at incredible speeds. But what makes supernova truly remarkable isn't just their destructive force, it's what they leave behind. In those searing temperatures and crushing pressures, something magical happens. The star forges elements far heavier than hydrogen or helium. Iron, gold, even uranium, these metals are born in the heart of the explosion, then flung across the cosmos like cosmic seeds. Take the Crab Nebula, for example. This swirling, filament-filled remnant is all that's left of a supernova witnessed by astronomers in the year 1054. Today, it's still expanding, its tendrils rich with newly minted elements. Without events like this, the universe would be a far simpler place, just hydrogen, helium, and trace amounts of lighter elements. There'd be no rocky planets like Earth, no oxygen to breathe, no gold to mine. Supernova are the reason your phone contains rare metals forged in stellar explosions billions of years ago. Every time you hold a piece of jewelry or even take a deep breath, you're interacting with stardust created in these violent final moments. Yet supernova aren't the only way stars contribute to the cosmic recycling program. Smaller stars like our Sun meet a gentler but no less important fate. Instead of exploding, they shed their outer layers in delicate, glowing shells known as planetary nebulae. Don't let the name fool you, these have nothing to do with planets. Early astronomers called them that because their round shapes resembled distant worlds through their telescopes. The Helix Nebula, for instance, looks like a giant eye staring back at us from space, its intricate rings of gas slowly dissipating into the void. Inside these glowing shells lies the star's exposed core, now a white dwarf, a dense, Earth-sized ember that will cool over billions of years. But before it fades, the star enriches its surroundings with carbon, nitrogen, and other elements crucial for life. Unlike supernova, planetary nebulae don't create heavy metals, but they do sprinkle space with the building blocks of organic molecules. Future stars born in these enriched clouds will inherit these elements, weaving them into new planets and perhaps one day new life. Together, supernova and planetary nebulae tell the story of how stars, in life and death, shape the chemical diversity of the cosmos. One is a thunderous finale, the other a slow, radiant exhale, but both ensure that nothing in the universe goes to waste. From the gold in your jewelry to the calcium in your bones, every atom heavier than hydrogen carries the echo of a star's final act. And as these elements mix back into nebulae, they set the stage for the next generation of stars, planets, and maybe even civilizations wondering, just as we do, where it all began. When a star like our Sun reaches the end of its life, it doesn't go out with a bang. It leaves behind something far more delicate and beautiful. Planetary nebulae are the universe's way of turning stellar goodbyes into breathtaking works of art. Imagine a star gently exhaling its outer layers over thousands of years, creating glowing, intricate shells that expand slowly into space. The Ring Nebula, with its perfect blue halo and wispy central details, shows just how precise this process can be. But what's really happening here, as the star exhausts its nuclear fuel, its core contracts into a white dwarf, a dense, Earth-sized remnant that will glow faintly for billions of years. Meanwhile, the outer layers drift away, lit up by the intense ultraviolet radiation from the exposed core. What makes planetary nebulae so fascinating is their sheer variety. Some, like the Helix Nebula, resemble giant cosmic eyes staring back at us, while others, like the Butterfly Nebula, stretch out in symmetrical wings of gas. These shapes aren't random, they're sculpted by the dying star's rotation, magnetic fields, and even companion stars orbiting nearby. The Southern Crab Nebula, for instance, looks like an hourglass with jets of material shooting from its poles, a testament to the complex dynamics at play during a star's final act. But these nebulae aren't just pretty to look at, they're crucial recyclers of cosmic material. The gas they release, enriched with carbon, nitrogen, and oxygen, mixes back into interstellar space, becoming part of future stars, planets, and possibly even life. Every carbon atom in your body likely passed through a planetary nebula at some point, forged in the heart of a dying star, and then set adrift to become part of something new. And here's something remarkable. Despite their name, planetary nebulae have nothing to do with planets. 18th century astronomers called them that because their round shapes resembled distant gas giants through early telescopes. The misnomer stuck even after we discovered their true nature. Today, we know these nebulae mark the transition between a star's life and its afterlife as a cooling white dwarf. They're a reminder that even in death, stars leave behind something luminous and lasting, a final gift to the cosmos before fading into darkness. Yet these glowing shells don't exist in isolation. As they expand, they collide with the surrounding interstellar medium, creating shockwaves that compress nearby gas and trigger new star formation. It's a gentle kind of cosmic feedback loop, one generation of stars enriching the next, ensuring the galaxy never runs out of raw material. And because planetary nebulae are relatively short-lived, lasting only a few tens of thousands of years, catching one in its full glory is like witnessing a rare and fleeting moment in the universe's grand timeline. The relationship between nebulae and star clusters is one of the universe's most captivating dances, a give and take of light, gas, and gravity that shapes entire regions of space. Look no further than the Pleiades, that glittering cluster of blue stars nestled within a delicate haze of dust. What appears as a simple grouping of stars is actually a snapshot of cosmic evolution in action. The nebula surrounding the Pleiades isn't just a backdrop, it's the remains of the very cloud that birthed these stars. Their intense radiation now scatters off the dust, creating that signature blue glow, a reflection nebula serving as both cradle and canvas. But this phase doesn't last forever. As the young stars grow stronger, their stellar winds rivers of charged particles streaming outward at millions of miles per hour begin pushing the surrounding gas away. Over millions of years, the nebula thins, dissipating into the void until only the star cluster remains. This is why we see older clusters like the Hyades standing alone, their natal clouds long since blown away. It's a reminder that nebulae are fleeting by cosmic standards, their beauty temporary compared to the enduring stars they leave behind. Yet even as they fade, these nebulae leave their mark. The trapezium cluster, embedded in the heart of the Orion Nebula, shows how stars and gas interact in real time. Here, massive young stars blast their surroundings with ultraviolet radiation, carving out cavities and triggering shock waves that compress nearby gas, ironically creating the conditions for even more stars to form. It's a stellar feedback loop. One generation of stars shapes the environment for the next. And then there's the Rosette Nebula, home to the dazzling NGC 2244 star cluster. This region reveals how clusters can literally hollow out their birth clouds. The combined radiation and winds from hundreds of stars have blown a colossal bubble in the nebula's center, leaving a ring of glowing gas encircling the cluster like a cosmic halo. Structures like these are more than just pretty, they're textbooks written in gas and light, teaching us how star clusters sculpt their surroundings over time. What's truly remarkable is how these interactions vary across the universe. In dense regions like the Tarantula Nebula within the Large Magellanic Cloud, clusters form so rapidly and intensely that their feedback creates sprawling networks of filaments and bubbles. Meanwhile, quieter nebulae give rise to smaller, more dispersed clusters, each telling a different story about the conditions of their birth. By comparing these environments, astronomers piece together how factors like gas density, turbulence, and even the presence of nearby supernova influence the fate of both stars and their natal clouds. For observers on Earth, these pairings offer some of the night sky's most rewarding sights. The Lagoon Nebula and its embedded cluster Messier 8 provide a stunning example, where dark dust lanes weave through glowing gas, punctuated by the sparkle of young stars. Through a telescope, it's like watching a live construction site, stars being built right before your eyes. And that's the magic of these cosmic duos. They don't just show us where stars come from. They reveal the dynamic, ever-changing nature of the universe itself, one where chaos and beauty are forever intertwined. The Orion Nebula is more than just a smudge of light in the night sky. It's a bustling stellar nursery, so close and bright that even ancient civilizations took note of its glow. Located just 1,500 light-years away, this cosmic cloud offers astronomers a front-row seat to star formation in action. Through telescopes, we can see newborn stars embedded in its swirling gases, their intense radiation ionizing the surrounding hydrogen and painting the nebula in vivid pinks and reds. But what truly sets Orion apart is its dynamic environment. The trapezium cluster, a group of young, massive stars at its heart, blasts out ultraviolet light and stellar winds that constantly reshape the nebula's structure, carving cavities and triggering new waves of star birth. It's a living, breathing ecosystem where gravity, radiation, and turbulence collide in an endless dance. Then there's the Eagle Nebula, immortalized by the Hubble Space Telescope's iconic Pillars of Creation image. Those towering columns of gas and dust aren't just photogenic, they're cosmic incubators. Hidden within their shadows, protostars are slowly gathering mass, shielded from the harsh radiation of nearby stars. But the pillars won't last forever. Recent observations suggest they're already being eroded by stellar winds, a reminder that even the most majestic structures in space are temporary. What makes the Eagle Nebula so valuable to scientists is its textbook example of feedback loops. The very stars born from these pillars will eventually destroy them, scattering material that may one day form new stellar generations. Far larger and more luminous than either Orion or the Eagle, the Carina Nebula is a cosmic powerhouse. Spanning over 300 light-years, it's home to some of the most massive stars known, including Eta Carinae, a volatile hypergiant that could explode as a supernova at any moment. These titanic stars flood Carina with intense radiation, sculpting its gas into fantastical shapes like the Mystic Mountain, a 3-light-year-tall pinnacle of dust and young stars. But Carina's real significance lies in its diversity. Here, astronomers can study every phase of stellar life, from fledgling protostars to dying giants, all within a single, sprawling complex. It's like a time-lapse of stellar evolution compressed into one dazzling region. What ties these three nebulae together isn't just their beauty, it's the way they serve as open-air laboratories. Orion teaches us about the chaotic early stages of star clusters. The Eagle reveals how radiation and gravity battle to shape star-forming regions. Carina shows the dramatic impact of massive stars on their surroundings. Together, they paint a fuller picture of how nebulae evolve, how stars are born, and how they ultimately alter their own birthplaces. And with each new observation, from Hubble to the James Webb Space Telescope, we're peeling back another layer of their secrets, seeing deeper into the dust, uncovering hidden stellar embryos, and even spotting the chemical signatures of future planetary systems. These iconic nebulae aren't just postcards from the cosmos. They're active, ever-changing chapters in the story of our universe. For centuries, nebulae were little more than fuzzy patches in astronomers' telescopes, mysterious clouds whose true nature remained just out of reach. Then came the Hubble Space Telescope, and everything changed. Its crystal-clear images, free from Earth's distorting atmosphere, revealed structures within these cosmic clouds that stunned scientists and the public alike. Suddenly, we could see the delicate tendrils of the Veil Nebula's supernova remnant in unprecedented detail, or count the individual newborn stars peppering the Orion Nebula's glowing gas. But Hubble was just the beginning. The James Webb Space Telescope, with its infrared eyes, peers straight through the dust that obscures visible light, uncovering stellar nurseries hidden within nebulae's darkest corners. Where Hubble showed us the surface beauty, Webb reveals the bones beneath the skeletal frameworks of star formation invisible to other instruments. Yet telescopes alone don't tell the whole story. Spectroscopy, splitting a nebula's light into its component wavelengths, acts like a cosmic barcode scanner, decoding the chemical fingerprints of distant gas clouds. Every element leaves a unique mark on the spectrum, allowing astronomers to identify substances like oxygen, nitrogen, or even complex molecules floating between the stars. This isn't just about cataloging ingredients. It's about understanding how these elements mix and interact. In the Tarantula Nebula, for example, spectroscopy revealed vast reservoirs of organic compounds, hinting at the raw materials available for future planetary systems. Ground-based observatories play a crucial role too. Giant telescopes like those in Chile's Atacama Desert use adaptive optics mirrors that flex in real time to cancel out atmospheric blurring, to capture razor-sharp images that rival space telescopes for detail. Meanwhile, radio telescopes like ALMA detect the faint whispers of cold gas and dust, mapping regions too chilly to glow in visible light. Together, these tools create a multidimensional portrait of nebulae, blending data across the electromagnetic spectrum to reveal processes no single instrument could capture alone. The real magic happens when we combine these observations with cutting-edge simulations. Supercomputers crunch the numbers, modeling how radiation shreds gas clouds, how shockwaves trigger star birth, or how magnetic fields shape nebulae into their intricate forms. These virtual laboratories let astronomers test theories at scales impossible in real life, rewinding time to watch a nebula evolve over millions of years, or speeding up collisions between stellar winds to see how bubbles form. When simulations match actual telescope data, like the intricate loops of the Cat's Eye Nebula, it's a sign we're getting the physics right, and the technological revolution isn't slowing down. New instruments like the upcoming extremely large telescope with its 39-meter mirror will probe nebulae in even finer detail, potentially spotting the faint glow of protoplanetary disks around infant stars. Space-based observatories planned for the next decade aim to analyze the atmospheres of exoplanets born in these clouds, searching for hints of life's building blocks. Every advance peels back another layer of the mystery, showing us that nebulae aren't just static scenery, they're dynamic, ever-changing engines of cosmic evolution. What's truly astonishing is how far we've come. The same nebula that appeared as a faint smudge through Galileo's primitive telescope now reveals its secrets in terabytes of data, chemical compositions, magnetic fields, even the subtle motions of gas filaments. Yet for all we've learned, each discovery raises new questions. How exactly do shockwaves from dying stars trigger new star formation? Why do some nebulae form intricate bipolar shapes while others sprawl irregularly? The answers lie waiting in the light, ready for the next generation of telescopes to uncover. Gravity may be the sculptor of the cosmos, but inside a nebula, it's locked in an eternal tug of war with other invisible forces. Picture a vast cloud of gas and dust, trillions of miles across, seemingly peaceful but seething with unseen battles. Gravity relentlessly pulls every particle inward, trying to collapse the cloud into dense knots. But thermal pressure pushes back as heated gas molecules bounce off one another like billiard balls, resisting compression. Then there's magnetic fields, weaving through the chaos like invisible puppet strings, guiding the flow of charged particles along their lines of force. This delicate balance determines whether a nebula will birth new stars or simply drift apart. Computer simulations reveal just how complex this interplay becomes. Take the famous star formation in turbulent molecular clouds. Project scientists fed equations representing gravity, pressure, and magnetism into supercomputers, then watched as virtual nebulae evolved over millions of simulated years. The results were astonishing. Turbulence, often overlooked, emerged as a key player. Like cream swirling in coffee, these chaotic motions created dense filaments where gravity could gain the upper hand, triggering star formation in unexpected pockets. Meanwhile, magnetic fields acted as cosmic brakes, slowing collapse in some regions while channeling material into others. Without these forces working in concert, nebulae might never form stars at all. Radiation adds another layer to this cosmic ballet. Young, massive stars don't just light up their surroundings, they blast them with ultraviolet photons and stellar winds, carving out cavities like blowtorches in butter. The Orion Nebula showcases this dramatically, where the trapezium cluster's radiation has hollowed out a bubble nearly 25 light-years across. Yet paradoxically, this destruction also creates shockwaves from these expanding bubbles compress nearby gas, triggering new rounds of star formation at their edges. It's a feedback loop written in physics. Stars alter their nurseries, which then birth the next generation under changed conditions. What's truly mind-bending is how these microscopic forces scale up. The same equations describing how air resists compression in a bicycle pump also govern the pressure balancing gravity in a nebula. Magnetism, generated by the slow churn of ionized gas, shapes structures from the tiny tendrils of the Veil Nebula to the vast, light-year-spanning pillars in Carina. Even turbulence follows universal patterns, whether in Earth's atmosphere or interstellar clouds. This universality is why studying nebulae isn't just about distant space, it's about understanding the fundamental laws that shape our entire reality. And the implications stretch far beyond star formation. The delicate dance of forces within nebulae seeds galaxies with the heavy elements needed for planets and life. Every time gravity wins a local battle, collapsing gas into a new star, it sets the stage for supernova that will later enrich future nebulae with carbon, oxygen, and iron. Magnetic fields, while invisible, guide these enriched materials into new configurations, potentially influencing where and how planetary systems form. Even turbulence, once seen as mere cosmic noise, is now recognized as a crucial architect of structure across the universe. The beauty lies in how these forces leave their signatures. The intricate loops of the Ring Nebula betray the presence of magnetic fields frozen into its expanding shell. The jagged edges of dark nebulae reveal where turbulence has dominated over gravity for now. And the glowing tendrils of Emission Nebulae, those are pressure maps showing where radiation has overpowered gas dynamics. By reading these subtle clues, astronomers reconstruct the physics shaping entire galaxies, one nebula at a time. What's next? As simulations grow more sophisticated, incorporating everything from cosmic rays to quantum effects, we're closing in on a unified theory of how nebulae evolve. Already, models can predict the formation of stellar clusters with eerie accuracy, matching telescope observations down to the placement of individual protostars. Yet mysteries remain. How exactly do magnetic fields couple with turbulence at microscopic scales? Why do some nebulae form stars efficiently while others seem stuck in limbo? Each answer unlocks deeper questions, proving that these cosmic clouds are far more than pretty space scenery. They're the universe's most dynamic physics laboratories. Nebulae are the unsung architects of galaxies, quietly shaping their homes in ways that ripple across cosmic time. Think of them as galactic engines, vast reservoirs of raw material that dictate where and how stars form, which in turn determines a galaxy's very identity. Take spiral galaxies like our Milky Way, where nebulae congregate along sweeping arms, their glowing tendrils tracing the blueprint for future stellar generations. These regions aren't just decorative, they're active construction zones where the cycle of star birth and death drives the galaxy's evolution. When massive stars explode as supernova, they don't just vanish, they send shockwaves through surrounding gas, compressing it into new stellar nurseries. This feedback loop ensures galaxies don't burn through their fuel all at once, but instead regulate star formation like a cosmic thermostat. The influence of nebulae extends far beyond their immediate surroundings. In starburst galaxies, places where star formation runs rampant, nebulae are the chaotic workshops fueling the frenzy. Here, collisions or close encounters between galaxies funnel vast amounts of gas into dense pockets, creating nebulae so prolific they birth stars hundreds of times faster than in quieter galaxies like our own. The resulting young, massive stars flood their surroundings with radiation, lighting up the nebulae like beacons visible across the universe. Yet this fireworks display comes at a cost. Such intense activity can blow away a galaxy's remaining gas, leaving it unable to form new stars in the future. It's a stark reminder that nebulae don't just create, they also set limits. Even in aging elliptical galaxies, where the vibrant spiral arms and glowing nebulae of their youth have long since faded, their legacy persists. The heavy elements forged in ancient nebulae, now locked in stars and planets, paint these galaxies with subtle chemical fingerprints. By studying these elements, astronomers can reconstruct a galaxy's history, much like geologists read layers of rock. The iron in an elliptical galaxy's stars, for instance, tells of countless supernovae that once erupted within its ancestral nebulae, enriching the galactic environment with metals over billions of years. What's truly fascinating is how nebulae contribute to the universe's large-scale structure. In galaxy clusters, the spaces between galaxies aren't empty, they're filled with hot, diffuse gas, much of which was once part of nebulae ejected by stellar winds or supernova. This intergalactic material, though invisible to the naked eye, acts as a reservoir for future star formation, slowly cooling and condensing until gravity pulls it back into galaxies. It's a cosmic recycling program on the grandest scale, with nebulae as the key intermediaries. The future of nebula research promises to unlock even deeper mysteries. Next-generation telescopes will peer into the hearts of distant galaxies, observing nebulae in various stages of evolution to piece together a more complete picture of galactic life cycles. Advanced simulations powered by machine learning will model how nebulae interact with dark matter, the invisible scaffold shaping galaxies, offering clues to how these luminous clouds influence the universe's hidden architecture. And as we discover more exoplanets, we're beginning to see how the chemical diversity seeded by nebulae might affect the potential for life elsewhere. After all, the same processes that forge the elements in your body are still at work today, scattered across countless nebulae in galaxies far beyond our own. This cosmic perspective shifts how we see nebulae not just as isolated marvels, but as vital players in the grand narrative of the universe. Their beauty is more than skin deep. It's woven into the fabric of space itself, a testament to the dynamic, ever-changing nature of creation. And as we continue to study them, we're not just uncovering the secrets of star formation, we're tracing the origins of everything. The next frontier in nebula exploration is already taking shape, with cutting-edge missions poised to revolutionize our understanding of these cosmic wonders. Leading the charge is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Unlike its predecessors, Roman will combine Hubble's sharp vision with an extraordinary field of view, 100 times wider than Hubble's infrared surveys. This means it could map entire star-forming regions in unprecedented detail, catching nebulae in the act of creating stellar systems. Scientists are particularly eager to study the earliest, coldest phases of star birth, when gas clouds are just beginning to collapse. These shadowy precursors to protostars, often hidden behind thick dust, have remained elusive until now. Roman's infrared eyes will peel back those dusty veils, revealing how turbulence, magnetic fields, and even dark matter influence a nebula's ability to spawn stars. Speaking of dark matter, its role in nebula dynamics is one of astronomy's biggest unsolved puzzles. While invisible, dark matter's gravitational pull shapes galaxies, and by extension, the nebulae within them. Upcoming missions like the European Space Agency's Euclid telescope will map dark matter's distribution around nebulae with precision, testing whether it acts as a hidden scaffold guiding star formation. Early simulations suggest dark matter may create subtle density variations in nebulae, like invisible fingers kneading dough, directing where gas condenses into stars. If proven, this could rewrite our models of how star clusters emerge from their cloudy origins. But it's not just hardware pushing boundaries. Artificial intelligence is transforming how we interpret nebula data. Machine learning algorithms now sift through terabytes of telescope observations, spotting patterns human eyes might miss. One groundbreaking project trained AI to recognize shockwaves in nebula gas, revealing previously overlooked sites of stellar feedback. Another uses neural networks to predict how young stars will influence their natal clouds over millennia, offering a sneak peek at nebulae's future evolution. As datasets grow, these tools will become indispensable, turning raw pixels into profound insights about cosmic chemistry and dynamics. The coming decade promises even more surprises. The James Webb Space Telescope's ongoing observations are already uncovering organic molecules in nebulae, complex carbon-based compounds that could seed future planets with life's building blocks. Meanwhile, ground-based telescopes like the Extremely Large Telescope will track the motions of individual stars within nebulae with unparalleled precision, showing how stellar siblings interact as they grow. And let's not forget citizen scientists' projects like Zooniverse enlist amateur astronomers to classify nebula features, proving that discovery isn't just for professionals. What ties these efforts together is a shared quest to understand nebulae not as static snapshots, but as dynamic ecosystems. Each mission, each algorithm, each new observation adds another piece to the puzzle of how these clouds shape and are shaped by the stars they create. The answers won't just illuminate distant gas clouds, they'll reveal how our own solar system began, and perhaps how countless others are forming right now across the cosmos. The tools may change, but the wonder remains that these glowing clouds hold secrets spanning from the birth of atoms to the fate of galaxies. Long before telescopes revealed their true nature, nebulae wove themselves into the fabric of human culture. Ancient civilizations mistook these glowing patches for celestial omens. The Greeks saw the Orion Nebula as the sword of a mighty hunter, while Polynesian navigators used the Magellanic Clouds as guiding markers across vast oceans. Fast forward to the Renaissance, and artists like Galileo's contemporary Adam Elsheimer painted the Milky Way with an almost prophetic accuracy, capturing its nebulous texture centuries before science confirmed its composition. But it was the 19th century that truly married nebulae to art, as romantic painters like John Martin depicted cosmic chaos with swirling, luminous skies that mirrored the nebular hypotheses of their time. These works weren't just decorative, they were attempts to grapple with humanity's place in an expanding universe. The 20th century catapulted nebulae into mainstream consciousness. Hubble's iconic images transformed them from fuzzy smudges into full-fledged cultural symbols. Vincent van Gogh's Starry Night suddenly felt less like abstraction and more like prophecy. Science fiction latched onto their otherworldly beauty, from the trippy nebulae of 2001: A Space Odyssey to the glittering backdrops of Star Trek, where these cosmic clouds became visual shorthand for exploration and mystery. Even music drew inspiration. Composer Gustav Holst's The Planet's Suite echoes the ethereal quality of nebular light, while David Bowie's Space Oddity captures their isolating grandeur. What makes nebulae resonate so deeply isn't just their visual splendor, it's their duality. They're both birthplaces and graveyards, chaos and order, science and poetry. Modern artists like Sophie Teuber-Arp and Anselm Kiefer incorporate nebula-like textures to explore themes of creation and destruction, while photographers blend Hubble's imagery with earthly landscapes, reminding us that the elements in those distant clouds are the same ones in our bones. This interplay reaches its peak in initiatives like NASA's Astronomy Picture of the Day, where nebulae are curated not just as data, but as art, complete with color palettes chosen to evoke emotion as much as to denote chemical composition. Yet perhaps the most profound cultural impact lies in how nebulae democratize wonder. A child gazing at a poster of the pillars of creation experiences the same awe as a PhD astronomer, proof that these cosmic clouds transcend language, age, and even scientific literacy. They've become universal symbols of curiosity, appearing on everything from album covers to protest banners, where their vastness hints at both humanity's smallness and its boundless potential. In an age of division, that shared wonder might be nebulae's greatest gift, a reminder that we all stem from the same stardust, spinning under the same shimmering skies. Now, let's turn to the mysteries still hidden within these glowing clouds, questions that push the limits of our understanding. How do magnetic fields precisely choreograph star formation within nebulae? Why do some stellar nurseries produce lavish clusters while others form only isolated stars? And what secrets lurk in the dark nebulae, those shadowy regions opaque even to our most advanced telescopes? Each unanswered question isn't just a scientific puzzle, it's an invitation to keep looking up, to keep wondering, just as those ancient stargazers did when they first traced constellations across the night. For all we've uncovered about nebulae, these cosmic clouds guard their secrets fiercely. Take magnetic fields, we know they thread through nebulae like invisible wires, but their exact role in star formation remains hotly debated. Some theories suggest they act as cosmic scaffolding, channeling gas into dense streams where gravity can take over. Others argue they might actually slow down star birth, resisting collapse like a hidden force field. The truth likely lies somewhere in between, with magnetic fields playing different roles depending on a nebula's size, temperature, and turbulence. Cutting-edge instruments like the Atacama Large Millimeter Array are finally allowing astronomers to map these fields in detail, revealing intricate patterns that could rewrite our models of stellar nurseries. Then there's the puzzle of what tips a stable gas cloud into collapse. Not every wisp of a nebula becomes a star, so what's the magic trigger? Supernova shockwaves were long thought to be the primary catalyst, but recent observations of isolated nebulae forming stars far from any explosions have complicated the picture. Cosmic rays, nearby stellar winds, or even the subtle gravitational nudges from passing dark matter clouds might all play a part. The Spitzer Space Telescope spotted one nebula where star formation seemed to ripple outward like dominoes, suggesting some collapses might spread through gas clouds like chain reactions. It's a reminder that these processes aren't just about brute force, they're about delicate thresholds being crossed. Perhaps the most visually striking mysteries are the bizarre shapes some nebulae take. Why does the Red Square Nebula resemble a perfect geometric figure, or the Boomerang Nebula mimic its namesake with near-symmetrical precision? Computer simulations show that binary star systems, jets of material, or even the rotation of the nebula itself can sculpt these odd forms, but matching specific shapes to their creators is like solving a cosmic crime scene. The Ant Nebula, with its eerie dual lobes, was recently found to harbor a hidden stellar dance at its center, two stars locked in orbit, their gravitational waltz carving the gas into that distinctive shape. Every strange curve tells a story, if we can just learn to read it. What's thrilling is how each discovery peels back another layer. When astronomers finally measured the magnetic fields inside the Orion Nebula's pillars, they didn't find the orderly lines predicted instead. The fields were tangled and chaotic, suggesting star formation might be messier than we thought. When the James Webb Telescope detected complex organic molecules in the Tarantula Nebula, it raised new questions about how chemistry intertwines with physics in these clouds. Even amateur astronomers contribute to the hunt, with backyard telescopes spotting subtle brightness changes that hint at newborn stars flaring to life. The more we learn, the clearer it becomes. Nebulae aren't just objects to study, they're dynamic puzzles, changing before our eyes and challenging us to think differently about the universe's grand design. And that's where you come in. Armed with nothing more than a modest telescope and a clear night sky, anyone can join this cosmic detective work. Some of the most beautiful nebulae, like Orion or the Lagoon, are bright enough to spot from suburban backyards, their gauzy glow revealing the same processes that built our solar system. With a few simple techniques like using oxygen-3 filters to enhance emission nebulae's red hues, or sketching subtle details to track changes over time, amateurs have actually contributed valuable data to professional studies. The next great nebula mystery might not be solved by a billion-dollar observatory, but by someone gazing upward in wonder, just as humans have done for millennia. After all, every expert was once a beginner, and every nebula holds stories waiting to be told. Stepping outside on a clear, moonless night with nothing more than a pair of binoculars, you're already equipped to witness one of the universe's greatest spectacles. The Orion Nebula, a glowing jewel in the hunter's sword, reveals its misty glow even through modest optics, a testament to how accessible cosmic wonders can be. But the real magic happens when you train a small telescope on it. Suddenly, that faint smudge resolves into swirling textures, with the trapezium cluster's young stars sparkling at its heart like diamonds set in pink velvet. Dark adaptation is your ally here. Giving your eyes 20 minutes to adjust transforms the view from "is that it?" to "how did I miss this before?" Location matters just as much as equipment. Escape light-polluted cities and the difference is staggering. Under truly dark skies, nebulae like the Lagoon or the North America Nebula emerge as ghostly shapes against the Milky Way's backdrop, no filters required. For suburban stargazers, narrowband filters, like an oxygen-3 filter, work miracles, boosting contrast by blocking unwanted wavelengths. It's like turning up the universe's brightness slider, revealing structures invisible moments before. Then there's astrophotography, where patience and technology unite to unveil colors our eyes can't perceive. A basic DSLR on a star tracker can capture the ethereal reds of hydrogen alpha emissions, while dedicated astronomy cameras tease out intricate dust lanes in nebulae like the Horsehead. The process is part art, part science, stacking dozens of exposures to combat noise, aligning frames with celestial precision, and processing the data to mirror what telescopes like Hubble see. Yet even a smartphone held to a telescope eyepiece can snap a recognizable image of Orion, proving you don't need expensive gear to start documenting the cosmos. What makes observing nebulae so profound isn't just their beauty, it's the visceral connection to the cosmic cycle. That faint glow in your eyepiece, it's the same light that left the nebula centuries ago, traveling across light years to reach your retina. The oxygen you're breathing, the iron in your blood, even the calcium in your bones were forged in stellar nurseries like these, then scattered by supernova before Earth existed. Every glance at a nebula is a direct line to our origins, a reminder that we're not just observers of the universe but products of it. And here's where the story gets even more compelling. Those same nebulae we admire for their artistry are also cosmic kitchens, brewing the ingredients for life itself. Complex organic molecules, from simple ethanol to the ringed structures of polycyclic aromatic hydrocarbons, have been detected floating in nebula clouds. The Rosette Nebula, for instance, harbors enough alcohol to fill a trillion cocktails. But more importantly, it contains the carbon-based compounds that could one day seed planets with life's building blocks. When we peer into these glowing clouds, we're not just seeing stars being born, we're witnessing the universe preparing the raw materials for biology on a galactic scale. Every atom in your body carries the echo of a stellar explosion: carbon in your cells, oxygen in your lungs, even the iron in your blood were forged in the hearts of dying stars and scattered across space by nebulae. These cosmic clouds don't just create stars, they're chemical factories synthesizing the very ingredients that make life possible. Take the Taurus molecular cloud, a cold, dark nebula where astronomers have detected over 150 complex organic molecules, from simple sugars to the precursors of amino acids. It's as if the universe is running its own chemistry experiments in these frigid, dust-shrouded laboratories, combining elements under conditions we're only beginning to understand. What's astonishing is how these raw materials travel. When a star like our Sun dies, it doesn't just vanish, it gently expels its outer layers, enriching nearby nebulae with carbon, nitrogen, and oxygen. Massive stars go even further, exploding as supernova to seed galaxies with heavier elements like phosphorus and sulfur. These elements hitch rides on stellar winds and shockwaves, eventually finding their way into new generations of stars and planets. The famous Eagle Nebula's pillars of creation aren't just incubators for stars, they're cosmic mixing bowls, stirring these life-giving elements into the next batch of planetary systems. Some of the most compelling evidence comes from meteorites, ancient space rocks that preserve the chemical fingerprints of their nebula origins. Inside them, scientists have found grains of stardust older than the Sun itself, along with organic compounds like adenine, a key component of DNA. This suggests the building blocks of life weren't just Earth's invention, they were part of the interstellar inventory long before our planet formed. Nebulae like Orion and Rho Ophiuchi are now known to harbor molecules like ethyl formate, which gives raspberries their scent, and vinyl alcohol, proving that the chemistry of life has universal roots. But how do these fragile molecules survive the violent chaos of space? The answer lies in nebula dust, microscopic grains of carbon, and silicates that act as protective shields. On their surfaces, atoms link up to form more complex structures, sheltered from harsh radiation. When these dust grains eventually clump together into comets or asteroids, they deliver their precious cargo to young planets. The water in Earth's oceans, the nitrogen in our atmosphere, even the phosphorus in our DNA might all have arrived via this cosmic courier system, with nebulae as the original source. This changes how we view our place in the universe. The same nebula that gave birth to our Sun likely also provided the raw materials for life's emergence. When we look at distant nebulae through telescopes, we're not just seeing stellar nurseries, we're glimpsing the universe's grand recycling program, where death begets creation on an unimaginable scale. And if nebulae could seed one small planet with life's ingredients, why not countless others? The implications are staggering. The story of life may not be unique to Earth, but written into the fabric of the cosmos itself, with nebulae as its prolific authors. Yet nebulae aren't frozen in time, they're dynamic entities with life cycles of their own. Some dissipate within a few million years, their material absorbed by new stars or blown away by stellar winds. Others merge with neighboring clouds, creating vast complexes where multiple generations of stars arise. The Cygnus X region, for instance, is a sprawling network of nebulae in our galaxy, where older stars have carved bubbles into the gas, triggering new rounds of star formation at their edges. Even as we speak, gravity and radiation are reshaping these clouds, ensuring the cosmic story of creation and destruction never ends. Nebulae aren't frozen in time, they're cosmic chameleons, constantly shifting form and function over millions of years. Picture a massive stellar nursery like the Orion Nebula, brimming with glowing gas and fledgling stars. In its youth, it's a bustling factory of star formation, but gravity and radiation are already sealing its fate. As newborn stars ignite, their fierce winds and ultraviolet light carve away at the surrounding gas like sculptors chiseling at marble. Over time, these forces hollow out the nebula, pushing its remaining material into delicate shells and filaments. What was once a dense cloud becomes a wispy network of ionized tendrils, barely clinging together against the void. Supernova add another twist to this life cycle. When massive stars, those born in the nebula's heyday, reach the end of their lives, they explode with enough force to send shockwaves rippling through space. These cataclysms inject fresh gas and heavy elements back into the environment, replenishing what star formation had consumed. The Crab Nebula is a textbook example, a supernova remnant still expanding nearly 1,000 years after the explosion, its filaments rich with newly forged elements. This recycled material doesn't go to waste, it mingles with other interstellar clouds, becoming part of future nebulae and future stars. It's a cosmic circle of life where death fuels new creation. But not all nebulae meet the same end. Planetary nebulae, like the Helix, tell a quieter story. These glowing shells are the final breath of sun-like stars, their outer layers gently expelled as the core shrinks into a white dwarf. Without the violence of a supernova, these nebulae fade more gracefully, their gas dissipating into space over tens of thousands of years, a blink in cosmic terms. Yet even in their dissolution, they leave a mark. The elements they release, carbon, nitrogen, oxygen, drift into the interstellar medium, enriching it for the next stellar generation. Compare this to nebulae in other galaxies, and the differences are striking. In the Large Magellanic Cloud, a satellite galaxy of the Milky Way, nebulae like the Tarantula are far more massive and prolific, birthing stars at a breakneck pace. The reason: lower metal content and weaker gravity allow gas to collapse more easily, creating supercharged stellar factories. Meanwhile, in elliptical galaxies where star formation has largely ceased, nebulae are rare relics, their gas long since blown away or locked up in aging stars. These variations aren't just curiosities, they're clues. By studying how nebulae behave in different galactic environments, astronomers piece together the life stories of galaxies themselves. The lesson is clear: nebulae are more than just waypoints in the universe, they're dynamic characters in an epic saga of creation and destruction. From the turbulent birth of stars to the quiet dispersal of planetary nebulae, their life cycles mirror the rhythms of the cosmos. And as we map these changes across galaxies, we're not just chronicling the fate of gas clouds, we're tracing the very pulse of cosmic evolution. While the Milky Way's nebulae dazzle us with their beauty, stepping outside our galactic neighborhood reveals an even more spectacular tapestry. The Tarantula Nebula in the Large Magellanic Cloud, a satellite galaxy orbiting our own, puts local star factories to shame. Stretching over 1,000 light-years and glowing with the intensity of millions of suns, it's the most active star-forming region in our cosmic backyard. What makes it extraordinary isn't just its size, but its raw productivity. While Orion might form a handful of stars every million years, the Tarantula births them by the hundreds, including some of the most massive stars ever recorded. Its core houses R136A1, a behemoth weighing over 250 times our Sun's mass, blasting out enough radiation to ionize gas clouds 50 times larger than typical Milky Way nebulae. Venturing farther afield, the Triangulum Galaxy's NGC 604 rivals the Tarantula in scale but tells a different story. Here, lower metal content, a legacy of fewer generations of past stars, creates nebulae with simpler chemistry yet astonishing clarity. Without heavy elements to absorb light, these clouds glow with an almost ethereal purity, their structures visible in stunning detail. Meanwhile, in the Andromeda Galaxy, astronomers have mapped vast networks of nebulae strung along spiral arms like pearls, each with distinct personalities shaped by their host galaxy's unique history. Some, like Andromeda's G1, show evidence of multiple epochs of star formation, their layers resembling tree rings that chronicle cosmic eras. What's revelatory about these extragalactic nebulae is how they challenge and confirm our theories. The same basic physics governs them all. Gravity collapses gas, radiation sculpts it, but subtle differences in environment create dramatic variations. Nebulae in small, metal-poor galaxies like the Small Magellanic Cloud form stars more efficiently, their pristine gas lacking the dust that normally slows collapse. In contrast, the densely packed nebulae of elliptical galaxies, where stars formed in frenzied bursts billions of years ago, now sit nearly dormant, their gas exhausted or blown away by ancient supernovae. These contrasts are gold mines for astronomers, offering natural experiments to test how factors like composition, pressure, and even dark matter density shape stellar birth. Perhaps most intriguing are the nebulae in colliding galaxies, like those in the antennae galaxies merger. Here, titanic forces compress gas clouds to extremes, igniting starbursts so intense they outshine entire galaxies. The resulting nebulae defy classification, neither the orderly spirals of isolated galaxies nor the calm halos of ellipticals, but frenetic, transient wonders. By studying them, we catch glimpses of the universe's youth, when such violent encounters were commonplace and galaxies built their first generations of stars. Yet amid this diversity, a universal truth emerges. Nebulae are the universe's great storytellers. Their shapes, colors, and chemistries encode the histories of their host galaxies, from quiet spirals to chaotic mergers. And as telescopes like JWST peer deeper into the cosmos, we're finding these narratives stretch back to the universe's infancy, where the very first nebulae devoid of heavy elements, yet brimming with raw potential, laid the groundwork for everything that followed. This grand perspective sets the stage for an even more intimate connection. The same processes that light up nebulae across the cosmos also create the conditions for planets, and perhaps life, to emerge. When we marvel at these distant clouds, we're not just witnessing star birth, we're seeing the cosmic factories that manufacture the ingredients of worlds. And that brings us to one of astronomy's most thrilling quests: how nebulae shape the search for exoplanets and what they reveal about the potential for life beyond Earth. Nebulae don't just craft stars, they are the universe's ultimate workshop for building planets. Hidden within these glowing clouds, swirling disks of gas and dust encircle newborn stars, spinning like cosmic pottery wheels as gravity molds them into planetary systems. These protoplanetary disks, some spanning distances greater than our entire solar system, are where the magic happens. Take the Orion Nebula's proplyds, short for protoplanetary disks, caught in stunning detail by Hubble. These pancake-shaped structures, backlit by the nebula's fierce radiation, reveal dark gaps where fledgling planets are likely carving their orbits, sweeping up dust and gas as they grow. It's a snapshot of our own solar system's infancy, frozen in time 4.5 billion years ago. But how does a featureless disk transform into diverse worlds? The process begins with microscopic dust grains, silicate, and carbon particles no larger than smoke. In the disk's chilly outer regions, these grains stick together through static electricity, forming fluffy snowballs of ice and rock. Closer to the star, where temperatures soar, only hardy minerals survive, creating the seeds of rocky planets like Earth. Over millions of years, countless collisions build these fragments into planetesimals, then protoplanets, until gravity takes over, sculpting them into spheres. The TRAPPIST-1 system, with its 7 Earth-sized worlds, likely arose from just such a disk, its planets neatly spaced like pearls on a string. What's astonishing is how much variety emerges from these seemingly uniform disks. Some nebulae, like the Taurus molecular cloud, produce disks rich in organic molecules, formaldehyde, methanol, even simple sugars, that could pepper young planets with life's raw materials. Others, near massive stars, have their disks shredded by radiation before planets can fully form, explaining why hot Jupiter gas giants sometimes orbit perilously close to their suns. The Eagle Nebula's pillars, famous for their star-forming prowess, also contain disks in their shadowy bases, sheltered from destructive ultraviolet rays. These cosmic incubators may be where the most stable, life-friendly planetary systems take shape. Yet the most tantalizing disks are those in Goldilocks zones, regions where water could persist as liquid on a planet's surface. In the Linz Dark Nebula 1251, astronomers have spotted young stars with disks spanning distances where Earth-like planets might one day orbit. Here, the chemistry is particularly promising. Radio telescopes have detected complex cyanide compounds swirling in these disks, hinting at probiotic chemistry in action. While we haven't found Earth's twin yet, each new disk studied adds another piece to the puzzle of how common or rare our world might be. This brings us to the dark nebulae, the universe's best-kept secrets. These dense, light-absorbing clouds might seem like cosmic dead ends, but they're actually stellar nurseries in disguise. By blocking external radiation, they create calm pockets where delicate protoplanetary disks can evolve undisturbed. The Coalsack Nebula, a pitch-black smudge against the Milky Way, is one such haven, its Inkai depths hiding countless fledgling stars and their potential planets. Infrared telescopes pierce this darkness, revealing disks at their most pristine, free from the destructive winds that plague brighter nebulae. In these shadowy cradles, the universe might be quietly assembling its next generation of habitable worlds, hidden from view but teeming with possibility. Dark nebulae are the universe's best-kept secrets, shadowy, brooding clouds so thick with dust they blot out the starlight behind them. To the naked eye, they appear as nothing more than voids in the Milky Way's glittering tapestry, like black ink spilled across a starry canvas. But hidden within these cosmic curtains, something extraordinary is happening. Behind the veil of dust, gravity is silently at work, pulling together particles of gas and dust into dense knots that will one day ignite as newborn stars. Without dark nebulae, we'd miss the earliest, most fragile stages of star birth, the moments when a wisp of gas first begins its slow collapse into a luminous sun. Infrared astronomy has torn away the obscuring layers, revealing the bustling activity inside these seemingly lifeless clouds. Unlike visible light, infrared wavelengths slip effortlessly through dust, allowing telescopes like NASA Spitzer and the James Webb Space Telescope to capture what our eyes cannot. What they've found is astonishing. Dark nebulae are anything but empty. Take the Coalsack Nebula, that iconic black smudge near the Southern Cross. In visible light, it's a featureless void, but infrared images expose it as a bustling stellar nursery, its depths speckled with protostars still swaddled in dusty cocoons. These infant stars, some barely 100,000 years old, are so young they haven't yet begun nuclear fusion. Their faint glow comes entirely from the heat of their gravitational collapse. What makes these shadowy realms so crucial to astronomy is their role as cosmic time capsules. Dark nebulae preserve conditions similar to those in the early universe, when the first stars flickered to life in similarly pristine clouds of gas. Without the heavy elements forged by later generations of stars, these primordial nebulae were simpler, colder, and far more efficient at forming massive stars. Studying modern dark nebulae gives us a proxy for that ancient era. helping unravel how the universe transitioned from darkness to light. The Pipe Nebula, another Inkai silhouette in Ophiuchus, offers a perfect laboratory. Its lack of turbulence and low metal content mirror the environment of the cosmos's first star-forming regions, letting astronomers test theories about those pioneering stellar births. Yet dark nebulae aren't just relics, they're active participants in galactic evolution. Their dense dust shields delicate molecules from destructive radiation, allowing complex chemistry to unfold. Radio telescopes have detected everything from simple water ice to the precursors of amino acids floating within these clouds. In the depths of the Taurus molecular cloud, vast reservoirs of methanol and formaldehyde hint at the organic richness available to nascent planetary systems. It's a reminder that the ingredients for life don't just emerge on planets, they're woven into the fabric of star-forming clouds long before planets even exist. The next frontier lies in understanding how these hidden factories influence their surroundings. While emission nebulae dazzle us with their glow, dark nebulae operate in stealth, their influence subtle but profound. As they spawn new stars, those stars will eventually light up and erode their birth clouds, creating the next generation of glowing nebulae. It's a cycle of concealment and revelation, with dark nebulae as the critical first act. And as astronomers develop ever more sensitive instruments, we're peeling back their mysteries layer by layer, revealing not just how stars form, but how the cosmos continually reinvents itself in the shadows. Long before telescopes unveiled their true nature, dark nebulae captivated humanity's imagination. Ancient cultures wove these cosmic voids into their myths, seeing them as celestial rivers, dragons, or portals to other realms. The indigenous Wardaman people of Australia, for instance, knew the coal sack as the head of the rainbow serpent, a creator spirit woven into the stars. Early European astronomers, lacking our modern tools, catalogued them as mere holes in the heavens, gaps where the Creator had neglected to place stars. It wasn't until the 18th century that scientists like William Herschel speculated they might be dark nebulosities, clouds obscuring the light behind them. This shift from myth to science mirrors our broader journey to understand the cosmos. What was once seen as absence is now known to be pregnant with possibility, a reminder that the universe's greatest wonders often hide in plain sight, waiting for the right tools and the right perspective to reveal their secrets. Long before the invention of telescopes, ancient skywatchers gazed up at those mysterious hazy patches, nebulae, and wove them into the fabric of their myths and understanding of the cosmos. Persian astronomer al-Sufi in the 10th century meticulously documented a small cloud in the constellation Andromeda, unknowingly recording what we now recognize as the Andromeda Galaxy, the closest spiral galaxy to our Milky Way. To the unaided eye, it was just another nebulous smudge among countless others, indistinguishable from the truly cloudy star-forming regions within our own galaxy. The Maori of New Zealand saw the Magellanic Clouds, two irregular dwarf galaxies, as the celestial anchors of their great canoe, while indigenous Australian stories describe the Coalsack Dark Nebula as the head of the rainbow serpent, a creator spirit winding through the stars. These interpretations weren't mere fantasy, they were humanity's first attempts to explain the unexplained, mapping the cosmos with the tools of story and observation. The true nature of these cosmic clouds remained shrouded in mystery until the 17th century, when Galileo's telescope revealed that some nebulae were actually clusters of stars too faint to resolve with the naked eye. Yet others, like the Orion Nebula, stubbornly refused to break into individual points of light, hinting at something far more enigmatic. Early astronomers like Charles Messier catalogued these fuzzy objects to avoid confusing them with comets, never suspecting that his list would one day become a roadmap to understanding stellar evolution. The Great Nebula in Andromeda, observed for centuries as a celestial curiosity, wasn't recognized as a separate galaxy until the 20th century, when Edwin Hubble measured its distance and shattered the notion that the Milky Way was the entire universe. What's remarkable about these early observations isn't just their inaccuracy by modern standards, but how they reveal the universal human drive to make sense of the cosmos. Whether viewed through the lens of mythology or the crude optics of early telescopes, nebulae have always provoked wonder and inquiry. They challenged the sharp divide between the celestial and the earthly, forcing thinkers to grapple with the idea that the heavens might be more dynamic and more mysterious than they appeared. The very word nebula, Latin for cloud, reflects this ancient confusion, a label born from an era when these objects defied categorization. Now, let's shift our gaze from history to the cutting edge, where nebulae continue to upend our understanding of physics. These cosmic clouds are far more than pretty backdrops. They're extreme laboratories where the laws of nature are stretched to their limits. Take the Crab Nebula, the remnant of a supernova observed in 1054. Its heart contains a pulsar spinning 30 times per second, emitting beams of radiation like a cosmic lighthouse. The energy here is so intense that particles are accelerated to nearly the speed of light, creating shocks that glow across the electromagnetic spectrum. Or consider the bizarre Red Square Nebula, with its near-perfect geometric symmetry, a shape so precise it seems to defy the chaotic nature of gas dynamics. At the quantum level, nebulae force us to rethink how matter behaves under conditions impossible to replicate on Earth. In the frigid depths of dark nebulae, temperatures plunge just a few degrees above absolute zero, allowing molecules to form on dust grains through processes that baffle chemists. Meanwhile, in the searing radiation fields around young stars, atoms are stripped of electrons and reassembled in ways that challenge our models of plasma physics. Even gravity itself behaves differently at nebula scales, where magnetic fields twist like invisible spiderwebs, guiding the collapse of gas into stars against all expectations. The more we study these environments, the clearer it becomes. Nebulae aren't just part of the universe's story. They're the pages on which the laws of physics are written, revised, and rewritten again. Nebulae serve as nature's ultimate physics labs, subjecting matter and energy to extremes impossible to replicate on Earth. Imagine a place where magnetic fields twist with the force of 1 trillion refrigerator magnets, where gas races at millions of miles per hour, and where temperatures swing from near absolute zero to millions of degrees within a single cloud. The Crab Nebula alone demonstrates this beautifully. Its heart contains a pulsar spinning 30 times per second, whipping charged particles into frenzied jets that glow across the entire electromagnetic spectrum. These conditions are so extreme they warp our understanding of plasma physics, showing how matter behaves when pushed beyond earthly limits. Take the bizarre case of the Boomerang Nebula, one of the coldest known places in the universe. Despite being energized by a dying star, its rapid expansion has chilled gases to just 1 degree above absolute zero, colder than even the depths of interstellar space. This defies intuition, proving how nebulae can turn known physics on its head. Meanwhile, in the heart of the Carina Nebula, radiation from massive stars like Eta Carinae rips electrons from atoms with such violence it creates glowing shockwaves visible light years away. These phenomena aren't just cosmic curiosities, they're stress tests for quantum mechanics and relativity, revealing gaps in our models that only such extreme environments can expose. Magnetic fields add another layer of complexity. In the Veil Nebula, filaments of ionized gas stretch across space like celestial brushstrokes, their shapes sculpted by invisible magnetic forces. Supercomputer simulations struggle to replicate these intricate patterns, hinting at undiscovered physics governing how fields interact with turbulent plasma. Similarly, the mysterious Red Square Nebula baffles scientists with its near-perfect geometric symmetry, a structure so precise it seems almost engineered, challenging assumptions about how chaos shapes cosmic clouds. But perhaps the most groundbreaking discoveries come from nebulae's role in particle acceleration. In the Cygnus loop, electrons surf on shockwaves at nearly light speed, emitting gamma rays that detectors on Earth can trace. These natural particle accelerators dwarf anything humans have built, offering clues about how the universe distributes energy across vast distances. Even dark nebulae, seemingly quiet, hide surprises. Their icy dust grains host chemical reactions that shouldn't occur at such frigid temperatures, suggesting quantum tunneling or other exotic processes at work. What makes these cosmic laboratories invaluable is their sheer unpredictability. Just when physicists think they've mapped the boundaries of known science, a nebula like Cassiopeia throws a curveball. Its supernova remnant glows with elements arranged in patterns that simulations can't yet explain. Or consider the Helix Nebula, where concentric gas rings imply pulses of mass ejection from its central star, a behavior not predicted by stellar evolution models. Each anomaly isn't just a puzzle, it's an invitation to rethink fundamental assumptions about how the universe operates. This constant push against the edges of understanding is what makes nebulae more than just pretty cosmic scenery. They're active participants in the scientific process, challenging us to refine, discard, or revolutionize theories we once took for granted. And as telescopes grow more powerful, these natural labs will keep serving up new mysteries, reminding us that the universe's greatest lessons often come wrapped in clouds of gas and starlight. Now let's follow the journey of that starlight and the matter it carries as we explore how nebulae recycle the very building blocks of the cosmos. The universe operates on a grand principle of sustainability, and nebulae are its master recyclers. Every atom heavier than hydrogen, the oxygen you breathe, the calcium in your bones, even the gold in your jewelry, was forged in the heart of a star and scattered into space by stellar winds or explosive supernova. These recycled materials don't simply vanish into the void. They're gathered up by nebulae, mixed with fresh hydrogen from the interstellar medium, and prepared for the next round of star formation. It's a cosmic loop that's been running for over 13 billion years, turning the ashes of dead stars into the building blocks of new worlds. Consider the life cycle of a single oxygen atom. Born in the fusion furnace of a massive star, it might spend millions of years trapped inside that star's core before being ejected during a supernova. Blasted across space at incredible speeds, it eventually joins a nebula, perhaps one like the Orion molecular cloud. There, gravity pulls it into a collapsing clump of gas, where it becomes part of a new star system. Some of that oxygen might end up in a protoplanetary disk, eventually forming water ice on a comet or the atmosphere of a young planet. This journey isn't theoretical. We've detected the chemical fingerprints of such recycled material in meteorites, which contain grains older than the sun itself. The scale of this recycling is staggering. A single supernova can expel enough heavy elements to seed thousands of future star systems. The Crab Nebula, for instance, is still expanding nearly 1,000 years after its star exploded, dispersing oxygen, carbon, and iron across dozens of light years. Meanwhile, gentler processes like the stellar winds of red giants slowly shedding their outer layers contribute lighter elements like nitrogen and helium. Planetary nebulae, often glowing with the vivid greens of doubly ionized oxygen, are particularly efficient at returning these enriched materials to the galactic ecosystem. What's remarkable is how this cycle maintains balance. Without nebulae to collect and concentrate scattered stardust, galaxies would quickly exhaust their star-forming fuel. Observations of distant galaxies show that those with prolific nebulae continue birthing new stars, while those where nebulae have been disrupted or stripped away, like many elliptical galaxies, become cosmic graveyards, their remaining stars aging without replacement. Our own Milky Way strikes a perfect equilibrium, with nebulae like the Carina and Eagle recycling material at a rate that sustains star formation without exhausting the supply. This brings us to the astonishing variety in nebula sizes and scales. Some, like the vast Tarantula Nebula in the Large Magellanic Cloud, sprawl across hundreds of light-years, birthing stars so massive they dwarf our Sun. Others, like the tiny, dense protoplanetary disks in the Orion Nebula, are mere specks in comparison, yet no less vital to the recycling chain. Even within a single nebula, scales vary dramatically. The pillars of creation in the Eagle Nebula stretch light-years tall, while the protostars forming within them are smaller than our solar system. The differences don't stop at size. Nebulae also vary wildly in density. Dark nebulae like the Coal Sack are so thick with dust they block all visible light, while emission nebulae like the Rosette are diffuse enough that their glowing gas stretches across vast distances with barely a star in sight. These variations aren't random, they reflect the nebula's role in the cosmic recycling chain. Dense nebulae shield delicate star-forming regions, while more diffuse ones allow radiation to escape, preventing runaway star formation that could deplete galactic resources too quickly. What ties them all together is their shared purpose: to gather, enrich, and redistribute the elements that make stars, planets, and life possible. From the smallest Bok globules to the largest supernova remnants, nebulae ensure the universe never runs out of raw material. They're proof that even in the vastness of space, nothing truly goes to waste. Every ending is just a prelude to a new beginning. The universe crafts nebulae in every conceivable size, from cosmic specks to sprawling giants that dwarf entire solar systems. Take Bok globules. These dense, dark pockets of gas and dust may span just a fraction of a light year, yet they're stellar incubators in miniature. Imagine a cloud so compact it could fit comfortably within the orbit of Pluto, yet massive enough to birth a star. Then there's the Helix Nebula, stretching nearly 3 light-years across, a dying star's final breath frozen in space, its intricate rings large enough to swallow our solar system whole. But these are mere pebbles compared to titans like the North American Nebula, covering an area 4 times the size of the full moon in our night sky. Its glowing hydrogen gas stretches over 100 light-years, so vast that under pristine dark skies, keen observers can spot its faint outline without optics. Even this pales next to supernova remnants like the Cygnus Loop, whose filamentary wreckage sprawls across 150 light-years, a testament to an explosion so violent its shockwaves still ripple outward after 20,000 years. Scale isn't just about bragging rights, it dictates a nebula's fate. Small, dense nebulae like Bok globules collapse efficiently under gravity, often forming solitary stars. Mid-sized emission nebulae, such as the Lagoon, become bustling stellar factories where stars form in clusters. The true leviathans, like the Tarantula Nebula in the Large Magellanic Cloud, operate on another level entirely. Spanning 1,000 light-years and birthing stars at a ferocious rate, their sheer size creates self-sustaining ecosystems where stellar winds and supernova trigger chain reactions of new star formation. Astronomers use these size categories like a cosmic ruler. Compact dark nebulae reveal the quiet beginnings of star formation, while the expansive glow of a planetary nebula chronicles a star's graceful exit. Supernova remnants, with their chaotic filaments, become natural particle accelerators for studying extreme physics. This classification isn't just academic, it helps decode how elements spread through galaxies, why some regions form stars explosively while others simmer slowly, and even how nebulae shape the evolution of their host galaxies. What's mesmerizing is how these scales translate visually through telescopes. The same pillars of creation that appear as towering columns in Hubble's iconic image would, if placed nearby, stretch farther than the distance between Earth and Alpha Centauri. Meanwhile, the delicate tendrils of the Veil Nebula, though fragile-looking in photos, are actually million-degree plasma waves wider than Orion's entire constellation. This disconnect between appearance and reality makes nebulae cosmic illusions, their beauty often masking unimaginable forces and dimensions. Yet for all their diversity, these clouds share a universal truth: their size is never permanent. A tiny Bok globule may one day expand into a radiant star cluster, while a vast supernova remnant will eventually disperse into invisibility. Even the grandest nebulae are fleeting by cosmic standards, ephemeral artworks in the universe's ever-changing gallery. Now let's unravel how these celestial marvels produce their mesmerizing light, a symphony of colors that tells the hidden story of their composition and energy. Nebulae aren't just visual wonders, they're cosmic chameleons, transforming their appearance depending on how we observe them. While our eyes perceive the vibrant reds and blues of visible light, these clouds radiate energy across the entire electromagnetic spectrum, each wavelength peeling back a different layer of their secrets. Radio telescopes, for instance, pierce through the obscuring dust of dark nebulae, mapping the faint whispers of cold hydrogen molecules too frigid to glow in optical light. It's like switching from a flashlight to thermal imaging. Suddenly, invisible structures emerge, revealing the intricate skeletons of star-forming regions. The Taurus molecular cloud, a seemingly empty patch of sky to optical telescopes, comes alive in radio waves, exposing vast reservoirs of gas where future solar systems are taking shape. Switch to infrared and the view shifts again. Here, the James Webb Space Telescope excels, capturing the warmth of dust grains heated by fledgling stars. The iconic pillars of creation, so dramatic in Hubble's visible light images, take on an ethereal new form in infrared, their dusty veils turning translucent, exposing the infant stars nestled within. Meanwhile, ultraviolet light exposes the most energetic action, highlighting the fierce radiation from massive stars as it ionizes surrounding gas. The Carina Nebula's ultraviolet portrait shows vast cavities blown by stellar winds, their edges glowing with the telltale signatures of elements like oxygen and nitrogen. But the real fireworks appear in X-rays. Chandra Observatory's images of nebulae like the Crab reveal superheated plasma, shock waves from supernova, and the frenetic activity around neutron stars. These high-energy emissions act like cosmic X-rays, probing the most violent processes within nebulae, particles accelerated to near light speed, gas heated to millions of degrees, and magnetic fields twisted into impossible configurations. Combine all these wavelengths, and nebulae transform from pretty pictures into multidimensional laboratories, where every layer of light tells a different chapter of the story. This multi-wavelength approach isn't just about aesthetics, it's revolutionizing our understanding of nebulae's role in one of astronomy's greatest mysteries, dark matter. While dark matter doesn't emit or absorb light, its gravitational influence leaves subtle fingerprints on the gas and dust within nebulae. By analyzing the motion of hydrogen clouds in radio data, or the distortion of nebulous structures in gravitational lensing surveys, astronomers hunt for discrepancies, telltale signs of dark matter's invisible pull. The Orion Nebula's outer regions, for example, show gas moving faster than visible matter alone can explain, hinting at unseen mass woven through the cloud. Some theories suggest dark matter particles could even collide and annihilate within nebulae, producing faint gamma-ray signals detectable by instruments like the Fermi telescope. While definitive proof remains elusive, nebulae serve as ideal testing grounds, their dense gas and complex dynamics amplifying any dark matter effects. It's a reminder that these luminous clouds are more than just stellar factories. They're cosmic scales weighing the invisible stuff that holds galaxies together. And as telescopes grow more sensitive across the spectrum, from radio arrays to gamma-ray detectors, nebulae may yet reveal the universe's darkest secrets hidden in plain sight. Nebulae glow with the light of ionized gas and scatter starlight through veils of dust, but their story may be shaped by something we can't see at all. Dark matter, that mysterious substance outweighing visible matter 5 to 1, likely weaves an invisible web through these cosmic clouds, subtly guiding their evolution. While telescopes show us the luminous ballet of nebula gases, the real choreographer might be this unseen gravitational force. Recent studies of star-forming regions reveal puzzling inconsistencies, gas moving faster than the visible mass should allow, filaments aligning in patterns that defy normal physics. These anomalies hint at dark matter's ghostly touch, its gravity sculpting nebulae from behind the cosmic curtain. Take the Orion Nebula's outer reaches, where hydrogen clouds stream at velocities that shouldn't be possible based on the stars we observe. Astronomers suspect dark matter's extra-gravitational pull could explain this discrepancy, acting like hidden anchors accelerating the gas. Similarly, the bizarrely uniform spacing of star-forming knots in the Carina Nebula's pillars resembles the predictable clustering seen in dark matter simulations. It's as if an unseen hand is portioning the gas into ideal stellar nurseries. Even the grand architecture of spiral galaxies, their nebula-studded arms perfectly traced, may owe their symmetry to dark matter's underlying scaffolding. The search for answers has led to innovative detection methods. By analyzing how background starlight distorts as it passes through nebulae, a technique called gravitational microlensing, scientists probe the mass distribution within these clouds. Any unexpected warping could betray dark matter's presence. Other teams hunt for faint gamma-ray glows, theorized to arise when dark matter particles collide and annihilate in dense nebula cores. While definitive proof remains elusive, nebulae offer a unique testing ground. Their turbulent environments amplify subtle gravitational effects, making them cosmic magnifying glasses for dark matter's faint signature. What makes this interplay so fascinating is its potential to solve two mysteries at once. Understanding how dark matter influences nebulae could reveal not just its nature, but also why some gas clouds collapse into stars more efficiently than others. Computer simulations that include dark matter's gravitational effects produce nebula structures eerily similar to Hubble's images, suggesting this invisible component may be the missing piece in star formation theories. The Horsehead Nebula's striking silhouette, the Eagle's towering pillars, even the delicate shells of Planetary nebulae might all bear the fingerprints of dark matter's invisible hand. This research is pushing telescopes to their limits. The upcoming Nancy Grace Roman Space Telescope will map nebulae in unprecedented detail, hunting for gravitational anomalies that could pinpoint dark matter concentrations. Meanwhile, the Vera Rubin Observatory's decade-long sky survey will track subtle motions within nebulae, creating the most comprehensive chart yet of their hidden mass. Each new dataset brings us closer to answering whether nebulae are merely bright tracers of a darker reality, cosmic lighthouses, illuminating the contours of the universe's greatest enigma. Now, let's turn from the invisible to the inspirational. How these glowing clouds are fueling humanity's boldest spacefaring ambitions. Nebulae aren't just objects of study, they're waypoints and resources for future interstellar voyages, offering both navigational markers and potential fuel for generations to come. Their allure stretches beyond science into the very dreams that propel us toward the stars. Nebulae represent more than just celestial marvels. They're the ultimate destinations on humanity's interstellar roadmap. While today's technology limits us to our solar system, visionaries already dream of sending probes through the glowing heart of Orion or skimming the turbulent edges of the Crab Nebula. Imagine a spacecraft no larger than a shoebox but packed with cutting-edge sensors, drifting through the pillars of creation, its instruments sampling primordial gas untouched since the dawn of stars. Such a mission would transform nebulae from distant spectacles into tangible frontiers, their chemistry and physics measured firsthand rather than inferred from light years away. The challenges are staggering but not insurmountable. Breakthrough Starshot, an initiative to send gram-scale nanocraft to Alpha Centauri, hints at how we might one day reach these cosmic clouds. A fleet of laser-propelled probes traveling at a fraction of light speed could intercept nebulae along their trajectories, transmitting data back to Earth over centuries. Picture them navigating the Tarantula Nebula's violent stellar winds or mapping the magnetic fields threading through the Veil Nebula's filaments. Even a fleeting passage would revolutionize astrophysics, offering ground truth measurements to refine our models of star birth and galactic evolution. What makes these hypothetical missions so compelling isn't just the science, it's the symbolism. Nebulae embody the scale and beauty of a universe waiting to be explored. They're the celestial equivalents of Earth's uncharted continents during the Age of Discovery, inviting us to venture beyond the familiar. A probe entering the Helix Nebula's glowing rings would do more than collect data. It would become a bridge between humanity and the cosmos, fulfilling a yearning as old as our first ancestors who gazed upward and wondered. Yet the true value of studying these distant clouds lies deeper. Nebulae remind us that we're not just observers of the universe, we're participants in its grand cycles. Every element in our bodies, every breath we take, was forged in stellar furnaces and scattered by nebulae long before Earth existed. When astronomers analyze the light from the Carina Nebula's violent star-forming regions, they're reading the same recipe that created our solar system. This connection transforms nebulae from abstract wonders into kin, their stories inseparably linked with our own. Contemplating these cosmic clouds also reshapes our sense of time. The Orion Nebula's infant stars, swaddled in gas, won't mature for millions of years. The Crab Nebula's expanding debris won't fully disperse for millennia. Against these timescales, human lifespans seem fleeting, yet our curiosity transcends them. The data we gather today might inform civilizations far in the future, just as we build upon the observations of ancient astronomers who first charted these hazy patches. Nebulae become waypoints not just in space, but in humanity's enduring quest to understand its place in the universe. This perspective shifts how we view exploration itself. Reaching a nebula isn't merely about crossing physical distance. It's about expanding the boundaries of human imagination and resilience. Each calculation of interstellar trajectories, each breakthrough in nanotechnology, each debate about what instruments to send, reflects our species' determination to touch the cosmos. Whether through robotic envoys or, one day, crewed ships, nebulae stand as beacons calling us forward, not just as destinations, but as milestones in an epic journey that began when the first star ignited from primordial darkness. When you gaze at the Orion Nebula through a backyard telescope, you're not just observing a distant cloud of gas, you're glimpsing a mirror reflecting your own origins. Every atom in your body, from the calcium in your bones to the iron in your blood, was forged in stellar furnaces and scattered across the galaxy by nebulae like this one. That breath you just took, its oxygen was cooked in the heart of a dying star billions of years ago, then swept up by a nebula to be recycled into the raw materials of our solar system. This isn't poetic metaphor, it's hard astrophysics. The carbon in your DNA, the nitrogen in your muscles, even the gold in your jewelry all share a cosmic birth certificate stamped by these glowing clouds. What's astonishing is how personal this connection becomes when you trace the journey. The hydrogen in the water you drink likely spent millions of years floating in a nebula before becoming part of a protoplanetary disk. The phosphorus that powers your cells might have surfed shockwaves from a supernova before landing in Earth's primordial soup. Even the rare earth metals in your smartphone were once stardust drifting through a nebula, waiting for gravity to sculpt them into a rocky planet. These elements didn't just pass through nebulae, they were shaped by them, carrying the chemical fingerprints of their turbulent histories. This shared lineage does more than satisfy scientific curiosity, it rewires how we see ourselves. In a universe where nebulae sculpt stars and planets with equal indifference, humanity's existence becomes both miraculous and humbling. The same forces that carved the pillars of creation also arranged the atoms in your fingertips. When Hubble captures the ethereal glow of the Carina Nebula, it's not just documenting a stellar nursery, it's archiving our ancestral home. That realization sparks something primal, a blend of awe and belonging that transcends culture or creed. Indigenous star lore, Renaissance art, and modern astrophysics all converge on this truth. We are the universe observing itself. Nebulae also serve as cosmic time machines, collapsing 13 billion years of history into a single frame. The light from the Eagle Nebula's pillars took 7,000 years to reach us, meaning we're seeing them as they appeared when humans first began recording history. Meanwhile, newly forming stars in the Orion Nebula represent what our Sun might have looked like in its infancy. These overlapping timelines create a profound perspective shift. Our lives, though fleeting on cosmic scales, are woven into a grand narrative that stretches from the first nebulae to the unknown future. This connection fuels more than philosophical wonder. It drives exploration. The same curiosity that compels us to study the Lagoon Nebula's chemistry also propels spacecraft beyond our solar system. When Voyager 1 turned its camera toward Earth from 4 billion miles away, capturing our planet as a pale blue dot, it echoed the perspective nebulae offer, a reminder of our smallness amid the vast and our responsibility as the universe's only known custodians of consciousness. Every image from the James Webb Space Telescope, every spectral analysis of nebula dust, is part of an unbroken chain of inquiry stretching back to the first humans who looked up and recognized those hazy patches as something extraordinary. As we conclude this journey through the cosmos's most dazzling clouds, let's revisit the milestones that make nebulae so captivating. From stellar nurseries where stars are born in violent beauty to the haunting remnants of supernova that scatter life's ingredients across space, these cosmic wonders are more than just celestial scenery. They're the universe's storytellers, chronicling how chaos gives birth to order, how death feeds new life, and how the simplest atoms transform into the building blocks of planets and people. The next time you see a nebula's glow, remember, you're not just looking at the universe, you're looking at where you came from and perhaps where we're all headed next. The future of nebula research burns brighter than the core of a newborn star, with groundbreaking missions poised to peel back even more of their secrets. The upcoming Nancy Grace Roman Space Telescope promises to map star-forming regions in unprecedented detail, acting like a cosmic ultrasound to peer into the earliest stages of stellar gestation. Its wide-field infrared capabilities will reveal how dark matter weaves through these clouds, potentially solving the mystery of why some nebulae collapse into stars while others linger as dormant gas. Meanwhile, the James Webb Space Telescope continues its revolutionary work, analyzing the chemical fingerprints of distant nebulae to understand how organic molecules, the precursors to life, spread through galaxies. But it's not just about bigger telescopes. A new generation of instruments is tackling nebula mysteries from unexpected angles. Quantum sensors being tested on Earth could one day detect the faintest magnetic fields threading through interstellar clouds, revealing how these invisible forces guide star birth. Artificial intelligence sifts through decades of nebula observations, spotting patterns human eyes might miss, like predicting where the next supernova might light up our galactic neighborhood. There's even talk of interstellar probes, conceptual missions that would send tiny spacecraft sailing through nebulae to sample their chemistry directly, like cosmic weather balloons reporting back from the storm fronts of star formation. What excites scientists most are the unanswered questions these tools might resolve. Why do some nebulae resemble perfect geometric shapes while others sprawl in chaotic splendor? How precisely do shockwaves from dying stars trigger new stellar generations? And perhaps most profound, could nebulae contain clues about physics beyond our current understanding? Some researchers speculate that certain oddities in nebula behavior might hint at exotic dark matter interactions or even undiscovered quantum phenomena playing out on interstellar scales. This isn't just academic curiosity, it's a quest to understand our origins. Every breakthrough in nebula research adds another piece to the puzzle of how hydrogen and starlight transformed into planets, oceans, and life. The same processes crafting nebulae today built our solar system billions of years ago, meaning these glowing clouds aren't just distant wonders, they're mirrors reflecting our cosmic ancestry. As technology advances, we're not merely observing nebulae, we're learning to read them like diaries, each page written in the language of chemistry, physics, and time. The most thrilling realization, however much we uncover, nebulae will always hold more mysteries. Their ever-changing forms and boundless complexity ensure they'll continue inspiring future generations, not just astronomers, but poets, engineers, and dreamers who see in their swirls both scientific marvel and artistic muse. Whether through a child's first telescope or a space observatory's billion-pixel sensor, that moment of connection when a fuzzy patch in the night sky resolves into a story of creation and destruction remains one of the most profound experiences our universe offers. And that's the true magic of nebulae. They invite everyone to witness the grand performance of cosmic evolution, no ticket required. Nebulae are the universe's grand storytellers, their swirling gases etching tales of creation and destruction across the cosmos. These luminous clouds are far more than celestial decoration. They're the factories where stars are born, the crucibles where elements forge, and the recycling centers that transform stellar death into new life. Every time we peer into the heart of a nebula, we're glimpsing the very processes that built our solar system, crafted the atoms in our bodies, and set the stage for life itself. From the violent nurseries of Orion to the delicate shells of planetary nebulae, these structures are cosmic clocks measuring the ebb and flow of galactic evolution over billions of years. What makes nebulae truly extraordinary is their dual nature, both destroyers and creators. A single supernova remnant like the Crab Nebula scatters enough heavy elements to seed thousands of future planets, while the gentle exhale of a dying sun-like star enriches space with carbon and oxygen. This cyclical dance of matter ensures that nothing in the universe is ever truly lost, only reshaped. The iron in your blood, the calcium in your bones, even the silicon in your smartphone, all were once stardust adrift in ancient nebulae, patiently waiting for gravity to sculpt them into something new. Our understanding of these cosmic clouds has skyrocketed thanks to telescopes like Hubble and James Webb, yet they remain full of mysteries. Why do some nebulae birth stars in frenzied bursts while others simmer slowly? How do magnetic fields sculpt their intricate shapes, and what role might dark matter play in their evolution? Each answered question reveals three more, proving that nebulae are inexhaustible wells of scientific wonder, but you don't need a PhD to appreciate their significance. Step outside on a clear night, and you can trace the faint glow of the Orion Nebula with binoculars, a direct link to the forces that shaped our existence. That simple act connects you to generations of stargazers who marveled at these same celestial wonders, and to future explorers who'll one day study nebulae from vantage points we can barely imagine. So keep looking up. The next great nebula discovery might come from a professional observatory or from someone in their backyard spotting a subtle change in a familiar cloud. The universe's story is still being written, and nebulae are its most vivid chapters. Share your own cosmic observations below and join us next time as we venture deeper into the cosmos's secrets. Until then, remember, every atom in your body was once part of this grand celestial dance, and the stars above still hold infinite stories waiting to be